This video we would be discussing how to read the pH chart or pressure enthalpy chart. Most designers they would memorize the compressor capacities or use catalogs for designing the systems. But a great idea is if we are able to read the pH chart, pressure enthalpy chart, that makes the entire design of the refrigeration system pretty easy. So today I will be showing you how to read the pressure enthalpy chart, not like a textbook, but like a diagnostic tool for evaporator and condenser design, compressor selection, and the expansion valve selection. So first, if you see a pH chart and if you are seeing it for the first time, you might panic. But it looks complex, but it is simple. See, it's simple because you see over here that it has only two axes. The x-axis where there is a enthalpy, specific enthalpy, it is denoted by H, and the unit is kilojoules per kg. So this is basically the energy contained which is being shown here. So you see that on this pH chart of R134A refrigerant, you have values like 100, 200, 300, 400, 500. So they are basically the specific enthalpy values. And on the y-axis, what you see directly is the pressure. This pressure is in logarithmic scale. Okay, so as you see over here, you see the pressure changing from 1 bar to 10 bar to 100 bar, and it is increasing in a logarithmic scale. It in a way pressure is useful because it is mapping directly with your evaporator temperature and condenser temperature. So for example, if you see in this diagram, the value of H1, okay, so 1 in my diagram is the inlet to the evaporator. So in the evaporator of the refrigerator, you'll find that the refrigerant is entering at state 1. In some books, you'll find that 1 is denoted as 4. So numbers are not fixed. You can name and start from anywhere because it is a cycle. But in my cycle here, H1 value, which you see as 238 kilojoules per kg, it reflects the specific enthalpy of the refrigerant which is entering the evaporator. Okay, and what you see is there is a straight line drawn from H1 to H2. Okay, where you see that the specific enthalpy is increasing from 238 kilojoules per kg up to 422 kilojoules per kg. Okay, and why is this enthalpy increasing? This specific enthalpy is increasing because of refrigerating effect. The refrigerant, it would absorb the heat from the space to be cooled in the evaporator section of the refrigeration system, and hence when it absorbs the heat from the space to be cooled in the evaporator, the enthalpy of the refrigerant in the evaporator would increase from, in this case, 238 kilojoules per kg up to 422 kilojoules per kg. Okay, what next? You'll find that there is a increase in the enthalpy in the from H2 to H3, right? And you see that it is shown as a slanting line. Now this slanting line, okay, it reflects the compression line. Okay, so you can say that the refrigerant which is entering the compressor would experience a change in enthalpy. There is an increase in enthalpy. In this case, you'll find that the enthalpy increases from 422 up to 500. Okay. Now, why is this enthalpy increasing? This enthalpy is increasing because you are supplying electricity to the compressor, you are supplying energy to the compressor, and as a result of which, the energy of the refrigerant would increase, right? Now, how do you get this value of H3? What you need to do is that at the outset, when you want to uh, find these values like H1, H2, H3, H4, what you need to do is that you need to draw two horizontal lines as you see what I had done here. So you see that there are two horizontal lines. One is called as PC and other is called as PE. PC is the pressure line which would correspond to the condenser pressure, and PE is the pressure line which would correspond to the evaporator pressure. Okay, so you see here that two horizontal lines are drawn, right? And the cycle would operate between these two pressures, evaporator pressure and condenser pressure. Condenser pressure is higher pressure, evaporator pressure is the lower pressure, right? How do you get the value of 2, 3, and 4? For that, you need to know two other parameters, one more parameter apart from the pressure, which is the temperature. Okay, for example, if I know the temperature at the outlet of the evaporator, okay, you see that those are the blue lines which you see over here in the diagram. These blue lines, they are reflecting the temperature lines. Okay, so as you see here at point 2 in this diagram, okay, the temperature line would correspond to some value which is higher than the evaporator temperature. So this is called a suction superheating. Okay, so H2, if you get, and if you draw a constant entropy line, a slanting line, okay, and reach 3, that is the exit of the compressor. Okay, and if you draw a horizontal again from 3 to 4, okay, that is a condenser line. Okay, condenser line, again the pressure remains constant, but the temperature would reduce, and then there is a phase change, and again there is a temperature reduction. Okay, so in the condenser you will find that the enthalpy is decreasing from in this case around 489 to 238. Why is this enthalpy decreasing from 489 to 238? The enthalpy is decreasing in the condenser because heat is being rejected in the condenser at a constant pressure. And you see the expansion line being drawn horizontal. Okay, that is, sorry, not horizontal, vertical. So in this diagram, 1 to 2 would represent evaporation, that is in the evaporator. 2 to 3 would represent what is happening in the compressor. 3 to 4 would represent what is happening in the condenser, and 4 to 1 would represent what is happening in the expansion device. So where does the enthalpy increase? The enthalpy would increase in the evaporator from 1 to 2. Then the enthalpy would increase in the compressor from 2 to 3. But the enthalpy would decrease and not increase in the condenser from 3 to 4, whereas there is no change in enthalpy in the expansion device, right? That is from 4 to 1. So this is how we can make use of the pressure enthalpy chart. You can read the pressure enthalpy chart for the calculations. Now what calculations we do? For example, if you want to calculate how much is the capacity of the evaporator coil, then we need to take the enthalpy difference across the evaporator. So for in my case, H2 minus H1. If I want to find the compressor capacity, I need to get the enthalpy difference between 3 and 2, H3 minus H2. If I want to get the duty of the condenser, that is how much capacity of the condenser is, then I need to get the enthalpy difference across the condenser. In this case, H3 minus H4. Okay, so this way, by knowing the specific enthalpies and multiplying the specific enthalpy change with mass flow rate, you can calculate, or you can design the evaporator, you can select the compressor, and you can design the condenser. So this introduction, I guess, is very important for understanding the design of a refrigeration.